note for your reference. You please keep your mic off at the time of deliberations, and whenever you feel any queries, you please raise your hands so that the queries can be taken, and accordingly those queries will be addressed. But please keep your mic off at the time of presentations.
Dr. Dipayan, may I start?
Yes. Yeah, please,
okay.
sir. Please, sir. Please, sir.
Okay.
Please, sir.
Okay, so thank you very much. And hello, everyone. Welcome to the course as the resilient control of the cyber physical systems. So as I introduced my name before, so my first name is Hamid Reza. The family name is Karimi. So I'm coming from the Department of Mechanical Engineering, Politecnico di Milano. So as already announced the schedule of the course, so today we have the two parts. The first part is about introduction to the network, to the CPS, and also some challenging topic we had in this context. So after that, I'm also trying to give another lecture about some control design based on for instance, the slide remote control. So let's look at the introduction part. So if you look at basically the introduction to the CPS. So
sir, sorry to interrupt you, sir. Your screen is not visible, sir.
It's not visible.
Yeah.
Okay. Is it okay now? Can you see my screen?
No, sir, it is not visible at my end.
Okay.
Participants, can you please confirm whether the screen is visible to your end or not?
Okay, I can share it again.
Yeah.
So
Yes, sir. Yes, sir. Yes, sir.
So can you see my screen now? Or?
Not yet, sir.
No, it is visible, Dr. Dipayan.
Okay.
The screen is coming.
Maybe it is not visible at my end, sir. Yeah.
It is visible, sir.
Okay.
Okay.
Sir, please, sir.
Okay, thank you. Okay, so the first part, I'm going to talk about the introduction to the topic of the CPS. And in this context, I'm looking at some challenging aspect in this area. So if we talk about the network control system or the topic of NCS, so we know that this system, it has a component including the physical plant, sensor integration, control design, actuator device, and also the communication networks. In this case, the systems are connected through the shared communication network.
Dear sir, you are unmuted, not unmuted. Your voice is not coming.
Okay, oh, sorry. So I think, let me ask you again. So is my screen visible and can you hear my voice?
Yes, now it is visible.
Okay, thank you. Okay, so I talk about the NCS as a starting point. So the NCS consists of a distributed plant and also sensor actuator integration. And of course, the task of the control, it consists of some sort of a sampling physical signals. We have a computational control design and actually implementing the signal through the actuator as a control input. So if you look at this structure of a distributed plan, so we can get some benefits as a remote access, remote operation, remote control, and also the context of the distribution of the system, and also the perhaps the low installation cost and also maintenance cost. Okay, so moving to the decentralized control in the context of the NCS is one of the emerging topic. But what could be some drawbacks in the NCS? So there could be some challenges is coming from the networks, including the time delay, limited bandwidths, and also the sending the data. And of course, we should expect some packet loss, the disorder, and so on. So you can see that the NCS potentially it consists of some challenges, and the main research in this context is to mitigate these kind of the challenges through the different control design or the scenarios. So beside of the NCS, we have a topic of the CPS as a cyber physical systems. So this is a topic basically we are focusing in this course. So the first thing that the CPS potentially can become the intelligence system. So basically by adding some software networks and also some adding to the cloud, it means that the CPS can communicate through the cloud. Now we have a cloud-based design, and also we have issues about the serious of industrial and information technology can be integrated in this system. So the system of the CPS, so they also call it as a basic integration of the physical and also the networks. And we have the issues about the computation, communication, and again, the control. So very similar to the context of the NCS, the network control system. Again, we have a basically the sensor positions, sensor selection, and also we need to look at basically the physical system itself. So the network the network also exists, and also we have issues about the cyber systems. So if you look at the CPS, so we can first of all about the system awareness, and also looking at the data sharing and also real-time analysis, and this kind of information so should be sent to some sort of the decision making for some the task of the system operation. So how the knowledge can be produced and how the knowledge can be circulated basically for the better execution or the operation of the system. Of course, the optimization is always the concern of the CPS. So now you can see that the circulation of the system operation for the CPS is based on the data, and this data, of course, should be transmitted through the networks and other physical aspect, including the sensor, actuator, and also the system itself is also exists. So now you can see that this kind of CPS potentially has given a lot of benefits from technology. At the same time, we should get a lot of concern in different aspects. So that's it. The topic of the CPS should be integrated with some other keywords, for instance, about the resiliency, about the security. So these are some issues that become very important from application side. So based on these scenarios, so we need to a little bit get a better understanding about basically the effect of each item, specifically about the data transmission. And I'm going to talk a little bit more about this topic in the introduction part. So now you can imagine that the many industrial aspects we can expect for the CPS, for instance, about some wastewater treatment plant. And this kind of the treatment plant, I'm sure that in India has also a lot of interest from application side. And this system, if you want, I can a little bit explain in more details later. So you can see that the system has different levels. So from the basically from the operation level or the human level and come to the system level, and this system is a quite distributed. You can see that it's a distributed system. There is a lot of subsystems, and how the knowledge of the expert, I'm talking about the owner of this plant, so could be sent some set point with a different subsystem. This is a very challenging topics. We have a network integration, then we need to look at the cybersecurity resilience. As you can see that this could be one example, and this example basically very important in different location and specifically for India. So another coming to the technology in the internet-based teleoperation. Again, we have a sort of the teleoperator as a master manipulator and also some slave manipulator. So this kind of the teleoperation, you can see that it can now become very emerging topic in the manufacturing and also in the health. In Italy, we have the big European project about the teleoperation for the surgery for the in the hospital. So you can see that in this context, because the data transmitted through the to this communication channel, and then we need to look at again the topic of the CPS and other basically the treats coming to the CPS, and then to see that how the signal could be healthy sent from the master to the slave part. So we can imagine that in all of these industrial applications, so the security and also the resilience of the system is of a high importance. So for this aspect, so for the NCS or CPS, so as we discussed before, there are three components: the plant, network, and the control. So the plant means that we need to have the information. Information means the modeling. If you have the model of the plant, then you can do the good analysis for the dynamics in terms of stabilization, and also you can do the monitoring of the plant. Of course, this information is very expensive and sometimes it's not possible to obtain it in advance. And that's it. The research in the CPS and NCS is moving from the model based to the data-driven approach. And that's it in my research group in Italy. So I have a research group on the data-driven control. In this scenario, so all the topic of the control design so should be managed through the data acquisition, and this is another research aspect. So the first thing we need to look at the network characterization, as including the network bandwidths, also to enhance the efficiency, and also look at some sort of the network induced constraint. So here I'm talking about the delay and also the packet dropout, and also the quantization, how to sample out the signal from the sensor to network and then to actuator. So this is a sort of a sampling. So in this course, I will talk about the event-based control. It means that you don't need to send all the data at the same time to the networks, because we need to save the bandwidth. If you want to improve the bandwidth, the topic, the approach is to move to the event-based control. And that's it. We are talking in another session about the event-based control design. Of course, the last but not least about the control. Control means improving the performance, stability, and also all the issues should be managed in the design. And that's it. In this course, we are talking a lot about the different control scenarios. For instance, a sliding mode control to get not only the fast response and also the limited time. It means in a finite time. So you should get basically the response with a good robustness. So now you can see that in the topic of CPS NC, it depends on your interest. If you want to touch to the modeling or touching to the network or the control, there is a lot of challenging topics. And of course, these are the matter of discussion. And depending on your interest, maybe we can discuss it. Even individual, you can contact me based on your interest, we can discuss in more details. So now you can see that there is a lot of interest to the NCS. So for instance, starting from 2007, so this was one of the important special issues published in the very good journal in the proceedings of the IEEE. So now you see that this issue published 12 papers. And in that time, they focus on the future trends in network real-time and wireless networks. And this was a very successful special issue. And then there was another special issue in the IEEE Control System magazine. And in this special issue, again in the same year, 2007, so the other important scholars, they put the topic of the complex network control system. And this is one of another opening the research line. So there could be other special issues from the application side. For instance, this special issue on the control of the networks and complex process systems in this journal of computer and chemical engineering. You see that these from the different from application side, from methodology side, the NCS becomes one of the important research areas after 2007. And for instance, the other special issues in the IEEE SMC Part C, so they open a special issue about the networking sensing control for the network control system architecture organ applications. So gradually this research become the hot topic. So again, the topic of you see that in IEEE TAC, it was also a special issue on the NCS. So they published 14 papers. So in 2004, now you can see that how many years back, so this research became the very hot topics. So, but in that time, so for instance, another journal, so they also, the network and control, they opened another special issue. So now I review some important special issue in the history of the basically the NCS. So up to now, so NCS has been developed a lot. There are many challenges, many the new topics has been added. So one of the new areas has been added is the resiliency about the cyber security, and that this becomes an important topic, and we try to basically discuss it in this course. So there are some important books about the network control system theory and applications. So there you can basically find some good result up to 2008 in the, as a state of the art. Okay, so when we talk again about the NCS, as I told you before, so we have one part, we have a plant, we have the controller, and we have the sensor actuators. So in the respect to the traditional approach, we have a point-to-point architecture. It means that the systems components are directly wired to the various controller. So this is a traditional approach to the point-to-point as a wire-based. But the development and the history of the control system, of course, coming from the analog control, centralized digital control system, moving to the decentralized control, and also FCS, the feed bus control and network control system. So in 1998 was introduced by Professor Walsh. And again, in 1988, also we had the integration of the communication control. But the keyboard of NCS was introduced in 98, but in fact, integration of the control and communication is back to 1988. But in that time, they talked about the partly digital design, partly analog control, and also completely distributed control. So these are some basically the progress of the control strategies in that time. So the definition of the NCS, so it means that the NCS is a completely distributed and network real-time feedback control. So now we can notice that distributed plant and also real-time control. It means that the integration of the physical process, the sensor actuators, and also controller through the communication networks. So this integration should be done in the real time. And this data transmission between the device, So this is one of the key aspects of the realization of NCS. So how we can realize the resource sharing, coordinating, manipulation, and also saving the bandwidth. These are the some topics we need to look at the data scheduling from the sensor, basically to the controller through the communication networks. So we have some typical NCS. So this is a model of a network control. So again, we have this kind of the plant. We have a controller. So we have the sensor and also coming to the networks and also send it to the controller for computation. Again, the data should be sent back to the actuators. So this is a typical NCS, and also at any position, again, we have a three parts: the plant, the network, and also the controller. Okay, so the traditional control, as I mentioned before, is a point-to-point control as a wire base. So this is a traditional control diagram. But if you want to take it to the NCS, so it means that we need to cut off the two data. So basically from the sensor to basically to the controller, and also controller, the signal has been computed to the actuators. So this is a network-based control. It means that both the measurements and control signals are sent over the communication networks. Okay, so now you see that the data acquisition control signal how to be sent, and the network characteristics are making the important role in these scenarios. Okay, so if you want to make it as the filtering part, as estimation, so the same issues we have for estimation or the filter design. For instance, if you have a physical plant, and if you have some sort of the input as like a noise or some other information, so if you look at the two kind of the data, so this is your signal, for example, as your target signal, and the signal Y could be the measure signal. Then you can see after filtering, so you can get the better estimation of this target signal, and then you will have the error signal. So in these scenarios, so we can see that this filtering part, it works based on if we could have a better filter design, and then the error signal could converge rapidly to zeros. So this could be the traditional, but if you want to take it over the networks, again, the data from the sensor should be sent through the network. So now you can see that the network-based filtering diagram, it means that the measurements are sent over the communication networks. So again, here is very similar to traditional approach because we are analyzing the error signal, but here what is the additive part is information of the networks, and this brings some challenge basically to the estimation part. Okay, so the advantage of NCS respect to the point-to-point interconnected control systems, the first thing is increasing the system reconfigurability. It means the scalability can be enhanced. So you can enhance the resource utilization, the reliability. So you see that the reliability can be enhanced in the context of NCS, because if you send less data to the event-based control, then basically the system performance can be enhanced with the saving the bandwidth. So reduce the installation, the maintenance cost, because for the wire point-to-point control, you can imagine how much cost goes for the installation part. But for the NCS, you can reduce, you can minimize the installation and also maintenance cost. So supporting the distributed control and intelligent device, it means that you can move to a smart control. It means that a smart device, a smart sensor. It means that the distributed control not only enhance the system resiliency, also they can also bring the opportunity to use a smart device. So based on these advantages, so the NCS becomes a very hot topics. And then there are a lot of research you can imagine for NCS. So if you look at the networks, network system, network device, control system. So all of these, they bring some gaps for the research. So for instance, if you look at the network control system through the network system, network device control systems, so we have a lot of issues about the stability and the performance. In the real-time processing, communication through the control applications, and also about the timing analysis, the modeling. We can expect many the issues for the NCS, and this is the reason that looking at this kind of research, we need to be specialized in some particular aspect, because the system relatively includes the huge amount of they need a huge amount of knowledge basically to look at the full control of the NCS. So the network system is classified as a data network and the control networks. For instance, if you look at the data network, so they depend on the size of the data packets. If the size is in the data network is large, so the frequency is infrequent, is sending the data to the networks. So but in the data network, so you see that the number of the nodes is relatively small. So if you copy the control network, so the size of the data packet is relatively small. You can frequently send the data, and also the system can be scaled up as a large number of the nodes, and also you can fulfill the time critical requirement. So this is some comparison between the existing data networks, basically structures, and compared to the control network architecture. So you can expect that in the control network, so you can basically you have a full basically you have a good flexibility. So on the scalability and also on the data security, because everything that you can control and based on your control strategy. And this means that in the NCS, the control strategy is very important, and this means that we need to pay more attention to this kind of control architecture. So about the key component of the control network, so about the network architecture, network protocols. So for instance, if we look at the network architecture from the sensor actuator level, and also cell control level, the plant management level, and coming to the corporate management levels. So for each part, we have some network protocol, for example, about the CAN, control area networks. So we see that about the Profibus, a feed bus, device, Ethernet. So based on the basic, the type of the basic network protocols, so this could be implemented for this part. So it means that for which architecture, so for example, sensor to actuator levels, so you can use a sensor bus. For example, the cell control, you can use a feed bus, and in the plant management, you can use the LAN. So it means that this kind of the network protocol is also part of basically the component of the control networks. So the network devices, we talk about the sensors, actuators. So we see that the data acquisition is important about how to move to the smart sensing or the sensorless. So if you are interested in one of the research topic in my group, is about the soft sensing. So in the soft sensing, we are looking at the sort of the prediction, also the measurements. It means that without using the physical device. But again, the data acquisition, communication ability, and intelligence is the basically the important aspect of the sensor and actuator. At least these are some important aspects. So when it comes to the controller, how to handle the decentralized information as well as the centralized information. So there could be a huge discussion how to move on from the centralized information to the decentralized. In some application, maybe we cannot achieve the fully decentralized. Maybe we need to look at the semi-decentralized, and that's it. there is another research aspect between the centralized and decentralized. We have something between as a semi-decentralized information. So how to handle this kind of information, and this could be also important topic if you are interested. So you can contact me because we have developed many sort of the semi-decentralized control for some particular application in control. But another topic is about HMI, the human machine interface. So to the operator and also the management level. So management level, these are the human knowledge. You see that the important topic in the CPS or NCS is how to get integrated the human knowledge or the management knowledge or operator knowledge based to the system operation. So this topic of the HMI, so nowadays in Industry 5.0, in Europe is one of the key topic, how to integrate, how to look at the interface between the human machine or the human robot, and this is a something. But there could be some other issues for like cognition, and that's it. If you are interested, so you can also look at some other topics, for example, about cognition. So, and that's it. In addition to HMI, so there is another topic is HMCI. So okay, another topic so could be, for instance, about the cognition. So if you look at the cognition, so for example, in the robotics, so this is also another interesting topic. And now there is another keyword as a HMCI. Okay. So the human machine cognition interface, HMCI. So but again, these are the very important topics. So nowadays in Europe, and we are talking about the industry 5.0. So in industry, if you are familiar with industry 4.0, in industry 5.0, so now the topic is about the HMCI. I think if you are interested, maybe we can discuss it later. Okay, so in the network device, so basically, as we discussed, we have a plant. Either you have a physical plant, you have a knowledge of the model, or if not, you have a data-driven model. So you need to look at the sensor and also actuator, basically the basic information or the device information. So there are two parts of the network. So here you can see that from the sensor to the controller, and also from controller to the actuators. So these two parts brings some challenge to this kind of the system operation, and that's it. We will discuss it more in details. So, for instance, in the control system, you can look at the direct structure. It means that in the direct structure means that the controller is between basically the first of all the sensor actuators are at the same side of the plant, but only the data from the sensor to controller to actuator goes through the networks. So this is basically the sensor measurement control signal, and this is we call it a direct structure. The direct structure means that the sensor actuator and also plant, they have this orientation. So another is the hierarchical structure is a bit different. So in the context of NCS, it means that for these scenarios of the plant and also the sensor and actuator you can see here, so there is a sort of the remote system between the sensor data measurement basically to the networks to the main controller. So now you're based on this kind of the data packet sending from the sensor measurement and also to the main controller and to send to the actuators. So there is also the one unit as a remote controller. So this remote controller, this also will be added to this remote system to the system operation. So this could be another architecture basically for the control system. But no matter which kind of structure we want to use, the challenge is the same. We need to look at the complexity of the networks. So in Italy, we have it, at least in our department in the mechanical engineering. So we have a very advanced laboratory. This laboratory is for the train. So if you are familiar with the train system, so each train system, so if you look at the train, so there is each car, it has two parts. There are two components. So two components as a wheel set. So this is one of these components, and then you can see that for the train, so that there are two such as the wheel set. So this name is a bogie. So the name of this device, if you are familiar with the train dynamics, so the name is a bogie. So you can search it. So bogie. So the bogie is basically for the transportation, basically for the wheel set of the train. So because India now is investing a lot on the train and basically for the intelligent transportation. So I would like to mention that one of the difficulties for the improving the technology in the railway is this device, because this device has a lot of sensor actuators and mechanical is very expensive, and how to look at the operation, how to look at control of this is a very challenging topic. So you can imagine that for the normal car, you know about the suspension system. So this bogie has a two suspension system. One suspension system here is a one suspension, and also another suspension system is connected to the car. So because of the complexity of this device, so there is one issues about how to control it, and that's the topic of the network control. So it's become as a modern railway. So if you want to look at this research about the diagnostic, about the monitoring, so I would like to mention that in Italy, so we are looking at the bogie control and also the how to control this device. So this is the pantograph. Pantograph is getting the electricity, is electricity to the train. Okay, this is for the power. This is for the power. So now you can imagine that if you move on to the modern railway, so you have the electricity from pantograph to the train. Here you have some Ethernet networks and you have some sort of the control of this device. So how we can manage to do it, because all the train can be controlled from the control room, from the CCR. So now you need to look at how to look at the train or to control and also monitoring diagnostics, and how to look at the operation of a different component on this device. So if in India your interest is on the rail and also on the technology for the train, and specifically to look at the control or to look at the cyber security for the such application, so you are very welcome to contact me, because our laboratory is a very advanced laboratory to look at the very complex challenges we have in this area. And this was information for you, because I know that India not investing a lot on the rail, and this could be one of the very challenging and important topics. Perhaps if you are interested, we can discuss in more details. So I personally teach this bogie from the modeling for the master students. But if you are interested, I can also give you some material about how to model this device, and how to look at the stability of this device. Because if the speed of the train, so one question for you is that if the speed of the train increase a lot, why the train is out of control? And this is one question. How we can look at the highest speed train? Highest speed train, what are the limitations? So if you are interested, I can also explain in one of the tutorial for you. Okay, so now you can see that in the topic of the NCS, so we have a lot of challenge. One topic is the signal transmission delay. So another topic could be the delay in the communication due to the buffering and propagation. So delay are bad for control loop. Delay can be fixed or the varying, either the measurable or the unknown delays. So data packet dropout, the network is unreliable. So the measurement is purposely dropped to stay within the allocated transmission rate. So we call it a congestion control. So now you can see that the data packet dropout, or do we look at the congestion control, signal quantization. These are some typical phenomena we have in the network environment. So from the delay to the congestion control to the signal quantization, so at least we can highlight these three important phenomena. So when coming to the signal sampling, so as we discussed, the data, so from the sensors to the controller to the networks, so this could be the normal sampling. It means that we have some sample data, and these are the three samples from your measurement YK, and this sample data can be sent basically to the controller node. Okay, so this is a signal YK. So for example, here you have a signal YK. So this signal can be sent to the controller, but now you can see that the data you can get at the control node, so a little bit shifted. Now you can see that this signal can be sent to here, and also this can be, for example, come to this position. So this is some sort of delay. So TKSC is the time delay between the sensor to the controller. So when you send again this data after the computation, based on the delay from the control to the actuators, there is another delay, TKCA. Now you can see that this sample data so can be shifted to the right. And again, this is also another basic delay can be added. So now the data is this is your sample data at this position is reached to the actuator. And then if you want to send the control signal, if you want to send this control signal, it could be like this. It means that the control signal can be updated at this time and not only at the sampling time k minus 1h. And if we look at here is a k plus 1h. So now you can see that the data can be updated at this time, and also the data control can be updated at this time. So this is the normal sampling. But let's look at another sampling as a vacant sampling and the packet loss. So the packet loss can bring some difficulties if, again, based on your sample data, for as we discussed before, this could be the YK. So let's look at the first time delay. So this is TKSC. So now you can see that if the TKSC is relatively large, basically for the first sample data, because the delay is a time varying. So in these scenarios, in the network, we have a time varying delay. So if this duration of the delay is relatively large, and then you can see that in this sampling from k minus 1h to kh, here there is no data, it's a zero data, okay? But here you have two data, one is the red and one is the green, and this means that some data has been lost, and this is a packet loss in this sampling time. But the system cannot send this red signal because the system can send only the green signal to that position. And now you have only two sample data. So what about the red sample data? So this data has been lost, and that's it. If you look at the control signal, for instance, here you have some vacant sampling. And if no information, if there is a zero information, means that the control signal cannot be updated. And that's it, the same control signal from the sampling k minus 2h. So in this sampling time, the signal is a constant and not update, and the signal can be updated only at this time. So this is a challenge. So this part is a challenge, and the first challenge is stability, because at this position, at this sampling, so at this position, so stability is a big concern, because how to guarantee how to guarantee the performance and control stability of the system. There is no any guarantee, and that's it. In the case of the packet loss, important issues is about stability, and we need to prove that the system can be, for example, can be stabilized. Stability, okay. So stability is one of the challenging topics. Okay, so now you can imagine that the NCS challenge and the solution. So basically, we can't. Okay, so there is one question. So yes, please. Okay. Do you have any question? Yes.
Yeah. Sir, I had a doubt that in the previous explanation, when one data is getting into the arena of the another data, so on the next step in the actuator node, how it is reduced to only one data in that time frame?
Okay, so good. So at this sampling time, because this red signal is a sample data coming from this K-1H, but the system is ordering. The system can react to this to the green signal, because here you could expect some congestion of the data. And that's it. The system so basically can react to the information of the green signal, because the red signal is out of use, and that's it. For instance, if you look at the sensor data from controller, from the sensor to the controller, so the green signal arrives at this position, and the signal can react to this signal. So this signal, in fact, is some packet has been lost, and also that has been rejected by the signal, because you know that the network has a sort of a delay. So it means that at this sampling time, we should expect that if we have a sort of the duration of the delay, and based on this delay, the system, the networks can send the data can be received at the controller point. So, and based on this time delay is already defined, or because of course one question is that how to know how much delay we have. So one research in the NCS, you need to get some estimation or some approximation, or some sort of the identification of the network delay. So, but of course we cannot get the exact delay, and that's it. The delay is bounded. There is a lower bound, upper bound, and also we have a sort of the basically the variation of the delay. So this red signal, the red sampling time, so this sample time, it arrives at the next sampling time, but of course it might be is out of the limit of the range of the delay, because at this position, for example, if we say that the TK, for example, the T at the sampling time TK is C, so it could be between the two is greater than eta 1 and is also less than eta 2, for example. So now you can see that you only know about this lower bound and upper bound. So this red signal, it might be is less than eta 1. And if the red signal is less than eta 1, the system cannot recognize. If the system cannot recognize this information, so this information will be rejected. And that's it. You cannot use this anymore. But there is another challenge. If this packet, this sampling time is appeared after the lower bound of the delay at for the sampling time TKSC, this is a very challenging topic, because now then you have a congestion. Then you have a two information, and that's it. We call this, there is a congestion information, and this is I didn't talk about this point, but you should your question is could be valid if the red sampling time it enters after the lower bound of the delay expectation at the sampling time TK. In this case, the congestion information is appeared. So now the question is that how fast this the signal can be can react is not basically we cannot have a good information about it, and this brings the less reliability. Okay, so when the congestion control has appeared, One of the problem is about the reliability, because reliability means that your control signal, you don't know the control signal has been updated at the which sampling time, at the sampling time based on the green or the red signals. And this lack of information, it brings the problem on the reliability. And that's it. In the congestion control, the big question is about stability again, because you cannot have a full control over the system operation. But very briefly, if the packet loss or the message rejection appear, for instance, for these scenarios, the big concern is stability, because we don't know how the system has been updated. So we don't know how the control signal has been updated. So this is a very challenging topic, and that's it. We need to move on to stochastic controls. Okay, so now maybe I at this moment I don't open the topic of stochastic control, because this signal, because this sampling time can arrive at any time. At any time, if you could accept some distribution profile for this sampling time. And this distribution profile could be some stochastic process. And that's it. If you want to talk about NCS with the packet loss, with the sort of this kind of the challenge, the system should be analyzed based on the probability base, stochastic base, and you can guarantee the stochastic stability of the system. So these are the some challenge. Of course, in the literature, you can find maybe a lot of result about this challenging topic. But yes, your question is a very important question, but the answer to your question depends if what is the timing about the arrival, the delay appearance in the next sampling, and this kind of the question, it opened the discussion about the stochastic stability. But of course, if you are interested, I can provide you some additional information about it. Do you have any other question?
Excuse me,
No,
sir.
sir. Thank you very much.
Okay, you're welcome. Yes. Any question? No?
Hello.
Yeah, hello. Yes. Please, okay.
Yes, can you tell me which are the distributions used for the stochastic modeling of the delay and this packet dropping kind of thing?
Yes, yes, I can. If you are interested, I can provide you some additional resources. But of course, I work on the NCS for many years, and also we also look at the sort of stochastic stability of the system, and this could be proven. But in fact, the important for the delay. So is the lack of information about the delay itself. And that's it. The only information you can expect is about the lower bound, upper bound, and you can do it with some tests. For instance, in my laboratory, students can do some tests on the network side, and they can get a better estimation about the delay information. Of course, the delay has been progressed a lot, and all the discussion on the delay is only how to get the better knowledge, and this better knowledge means how to model it. But in fact, in the NCS research, so the delay also the connected to the data, the sending and receiving over the network, and the networks it could filter some data in some sampling point like this. And then this kind of the missing the data depends on the duration of the delay. So this means that we need to look at some probabilistic basic feature of the sampling time for coming to the sort of the stochasticness. So these are some issues. Basically, you can find many state of the art in this area. But as I told you before, that the time delay in the network is one of the key issues, and because we are looking at the quality of control, this topic is exactly shows how is the quality. The quality means the performance. On the top of that is the stability. So that's it. Here the big challenge is how we can guarantee stability with such the challenging aspect in the message rejection of the packet loss. Okay, so any other question? Or?
Okay, thank you, sir.
Thank you. Okay, so I think for the NCS challenge, as based on the good question you mentioned, you see that always stability is the first. It means that we need to basically to look at stability and also delay compensation. So these are the basic two important topics. Always come first. And the second after stability is coming to the performance enhancement. It means that how we can look at the bandwidth allocation scheduling. And for this topic, basically for this topic, I will talk about I will discuss about event-based control, and this is a topic we have in this course. So network security, and I will give you one tutorial about the security for the connected cars, because in my research group, there are some PhD students, they work on the security or the cyber security for the autonomous cars. And I can show you some result about the network security for the cars. So again, you can see that another challenge is integration of component and distribution of intelligence. So these topics coming to the machine learning, AI, and how the machine learning can be integrated to NCS. So of course, one of the benefits of machine learning is for the monitoring, and that's it. In my research group, one of the group is the condition monitoring. So we are looking at the condition monitoring, basically the monitoring of the system operation from the sensor, actuator, or the whole system components for mechanical, for electrical. So now you can see that there is a huge amount of the challenge we have in NCS. Of course, we have solutions. So in this course, we want to give you some challenge, and of course, we want to provide you solution. But of course, we cannot expect that we can handle all the challenge, because the research and the teaching are integrated. So in this course, we are opening some important topics, some challenge, and we try to address some solution. Of course, it depends on your interest, depends on your research profile. So you could expect maybe some other challenge, and we need to look at other solution for your problem. And that's it. When we talk about the CPS, NCS, we need to look at application. So in the future, if you have some particular application in mind, so please let us know, and then we can discuss more specifically, because nowadays there are many applications you can imagine, and this is a very important, this kind of the research, they can bring you to some practical technology aspect. And if you are working the robotics on the robot networks, or you work on the autonomous cars, or whatever you are focusing on your research profile, so we can discuss, because the research come from application in these particular areas. So about the delay, so just for your information, that I did work many years on some sort of manufacturing. So manufacturing, of course, in India also there is some research universities or the companies very deeply focus on the cutting process. So the cutting process nowadays is doing on the network, because all the machines, they work on the sort of the network base. So for your information, this is the one example if you want to see how the delay is appeared in the cutting process. So here you have a workpiece, and this workpiece, there is a cutter. You see the cutter, they try to basically make a surface. So this cutter has some suspended mechanism in X and Y. This is a two dimension, and with the speed of the omega, it try to rotate, and then you try to basically control it by applying the particular input signal, and then you generate the surface. So what is the problem? The problem is that so this system can be modeled as a spring and damper vibratory model. It means that this system is a two-dimension. So you have the forces in the direction x, fx, fy, and these two forces, so they can be modeled. So based on the spring and mass and damping. So here you have a based on acceleration, velocity, and also position in the x, the position in the y axis. This should be y dot. So this should be y dot, and this acceleration. So mx is the inertia, cx is the damping. So the cs is a damping, and the kx is for a spring. You see that this is a spring for a stiffness. So now here you have a damping. So I can write it here. So you have a damping, and also you have a stiffness. So a stiffness, so basically is for the parameter f. So a stiffness, okay? Okay, so if you look at the two forces, Fx and Fy, and based on this mathematical model, then if you start to look at the surface can be generated. So here is the same problem, you see? So here you have a two forces, here you have a two forces, you can see. And this is exactly the same X and Y, and this cutter starts to rotate. So at this position, if you look at this position, is the tip position of the cutter start to touch the surface. Okay, so this area, so this area, oh sorry, so this area can be modeled like this. So like this point, it means that the cutter they touch the surface, but there is some oscillation, you see, and this oscillation means the quality. If you want to get the good quality for the good surface, so you need to have a much more soft, a smooth surface. And why the surface is not a good quality? Because of vibration. And that's it, the topic of the vibration. It very important topics. And in this particular case, you need to know that how to mathematicize the delay. So I think one of you asked me about the delay. I want to tell you that in this particular application, so if you try to mathematicize the model, so about the chip thickness encountering the bitutes, it means that here you can see that there is some vibration at the touching point. So here you can write some mathematical function basically for the deviation of the delta x. It means that the delta x is the xt minus t, and delta y is the y minus yt minus t. So now you can see that the delay or the parameter t depends to some parameter like a rotational speed and also the number of teeth. Okay, so how many teeth is on this cutter? And also you see the z is the number of the teeth of the cutter. And also the omega is the speed of the rotation, of the cutter. Okay, so now in the practical application, so the delay, for example, this delay you can see there is a model like this, and based on that, you can basically find the speed of the spindle. So this was the one example for you to see that in practical application, so you could expect a delay. So one source of the delay could be the network or could be some issues about the vibration. And this example was exactly presenting this point. So for this cutting process, if you want to start to make a model, so here is a dynamical cutting force. So this is a dynamical cutting force. It's a mechanical model, as I showed you before. You have a two force Fx, you have a force Fy. So, but the point is that you can develop, because the model is fully nonlinear, and then based on the vibration and the cutter, so you can get the two forces. You can develop some transfer function after some linearization in the linear form. You can obtain some transfer function with frequency. So usually because the system is a two-dimension, because this system is a two-dimension, is a 2D, so you can get the four transfer function. You can see. So this four transfer function is appeared here. Okay, so you can also obtain some transfer function as a direct and cross transfer function. So these are some function that you can obtain, but I'm not going to much detail, but just I want to show the main idea. This transfer function, so here you can see that there is a sort of the delay is appeared as a parameter t, because my focus is about the t. So this the delay is appeared in the sampling time. So in the Laplace transform, you can get this exponential term. Okay. This exponential term is represented that this is your ideal transfer function, and this is the transfer function after the vibration effects. So if you look at this signal delta x, delta y as an error signal at this position, so you can obtain basically this kind of the information in the frequency. But okay, so this is about the appearance of the delay. So, but in this case, if the delay is appeared because this exponential term should be added to the model, then you need to add this exponential term for the delay. So now the delay is appeared in your transfer functions, and then what you need to do, you need to design the control and to compensate the delay. And so now the topic of the delay compensation is important. But in this application, so you know exactly the delay because I showed you how to calculate it. And then the next step is to design the control. And this was one of the projects we did some years ago. And if you're interested to some sort of the application in this area, so you can contact me. So another project we did also is important for India because India is a large country. One of the big challenges is the production networks. So production networks is also something like the network control system is distributed, is a large networks. But the point is that in this application, so if you look at the picture on the right, you have several autonomous working systems. They work in the autonomous way. But in the production networks, you get some set points. So this is set point as basically some orders. So they want to give it to the networks. And then the VIP is the work in progress. It means that the VIP shows the capacity. VIP is the capacity of the networks. Okay, so in the production networks, one item is the model of the network, is the autonomous system. You can see they are connected. So this autonomous system in India could be the production network for some goods. For example, they are producing some goods, or even they are producing the fruit, for example, or transportation of the fruit from south of India to the north of India. It means that you have a large production network. So there are a lot of autonomous working systems and they are connected. But the point is that you get some order. If you get the order, the system should start to operate, and the system will look at some sort of the work in progress VIP as some sort of in the system. And finally, you can get the order flow out. It means that you need to get this order flow. But in the production networks, in this project we did some years ago, we look at these issues about the total number of the input orders is coming to each station or WI. This is the dynamical model of the orders to the system. A total number of the output orders, omega O, and also VIP is the capacity, is the work in progress of the system, and also the actual capacity. But very important thing is that if you work in the production networks, So the capacity of the network is become nonlinear, and also there is some delays. So now you see that some orders can be stored in the station and then send it after some time, or some order arrives late. It means that this capacity function, for example, depends on the delay. It's between some B1, B2. It means that we should expect some sort of the delay in the capacity of each station, because they cannot react in real time. If some order arrives, it should be stored, and after a few days or a few weeks can be sent it out. So now, if you imagine that you work in the production network for the food in industry in India, so one question is that how is the model of the capacity of each station? How many about the delay is appeared? And about the network of the production system, autonomous system. And what we did in this project, I did it with Germany. So this project was for the food industry in Germany. So now you can see that you can get understanding about the delays and also delay compensation. And this is the autonomous system, and perhaps depends on your interest, you can use it. Okay, so because of time, so I talk about this, but I want to switch to one topic. Basically, is very important. So as a basically just a moment.
Excuse me, sir. Can you share your
Yes,
slides?
yes, sure. I want to start the second lecture because do you have any question about the first part or?
If you kindly share the slides, it will be great for us.
Oh, sure, sure. I will send you all the material through the course coordinator.
Okay. Thank you, sir.
Okay, thank you. Okay, so the second part I want to discuss basically is about the design issues for control systems. So for this part, I would like to tell you a little bit more about the design issues for control. So one topic is about stability, and we discussed before. So today we noticed that we focus basically on the sense, on the actuator, on the system, and also on the sensor model. But here, based on your the data acquisition sensor data, and also based on the reference signal, so perhaps you could think about the performance and also stability. So for the stability and also the performance, how is the system is capable to follow the reference signal? Because one topic is about the reference tracking or adaptive control. It means that how to reduce effect of the measurement noise. So we have a noise, we have some uncertainty in the model. So all these topics you need to look at in the design. When you design the control, first is stability, the second is the performance. The performance, it reflects the noise issues, uncertainty in the modeling, the disturbance, or even the reference tracking. So now if you design the control, perhaps you think about the feedback control. The feedback control, it means to enhance the stability. At the same time, you can think about the feed-forward control. The feed-forward control also basically can be useful basically for the enhancement of the performance. So that's it. Here you have a two control signal, and these two control signal, basically one is the feed-forward control, another is the feedback control, and the total control become the US. Okay, so this control signal can be applied. Okay, so if you think that the system is ideal, if the system is ideal, you can expect that the model of the sensor and actuator is identity. Okay, so for this identical, the sensor actuators with this function one, so you have this typical system, and this typical system, you have a noise in the sensor noise, you have a disturbance actuators, and also you have some issues about the error signal. You need to bring it to for the convergence. This should approach the zeros. At the same time, you need to look at the effect of the noise and also the disturbance. So for this particular case, if you want to start to analyze, so there are several transfer functions you can obtain it. So this transfer function, the first is a signal XS, so you can basically calculate it from this function. And also you can obtain the control signal US basically. So from this function and also the YS is contain the noise. Okay, so if you look at this model of this system in the Laplace domain, in the frequency domain, you can see that the noise is appeared here, and also the disturbance DS is also appeared in your case. Okay, so now the important thing is that if you want to get a better control signal US, so your control signal should mitigate effect of the noise, effect of the disturbance, but the problem is that the noise is appeared in the information Y, and that's it, the amount of the noise, how to look at the noise compensation. So this is one of the challenging topics we have basically in the design issue. So, but the point is that for this system with the three inputs, because here we have a three inputs, we have a noise, we have a disturbance, and also we have a reference signal. There are three information as an input signal. And then the relation between the three information and also to the three outputs, one is the XS and also Y and also US. These are the three interested signal. So one interested signal is a state of the system XS, another is the measure signal YS, another is the input signal US. But the point is that here you will get the 9 transfer function, because in this system, in total, you have a 9. So in total, you will get the 9. So in total, you have a 9 transfer function, okay? So now the question is that if you want to design control, because only you can do it is to design the RS, because you need to design the control signal RS, and then you need to pay attention that how to design it in such a way that reference signal should be appear in the YS. It means that you need to do the tracking. If you want to do the good tracking, the error signal should go to 0. At the same time, you need to mitigate effect of the disturbance, effect of the noise. And then everything should be based on this 9 transfer function. And now the design is how to basically to design the optimal solution for this problem. Okay, so there is a lot of analysis in the state of the art for this part. So one thing is that we need to find the transfer function LS. This is a closed loop transfer function, or we call it the complementary sensitivity function. Okay, so this function is the first function should be designed, and the second is a sensitivity function, SS. So this sensitivity function is sensitive to the noise. Basically, you can develop it. For example, for the noise sensitivity function Sn, or the load the disturbance sensitivity function SL. Okay, so if you look at here that the function Sn is represent also effect of the noise. So you need to mitigate the, for example, Sn should go to become less, Ls should increase. So in fact, you need to increase Ls, for example, Ls to 1. If you want to increase Ls, at the same time, you can see that Ls is multiplied by ds, and then this also increase the effect of ds. So now there is a trade-off. Okay, so if you want to design the control, there is a trade-off between Ls, SNS, and SLS. At the same time, you need to find a suitable control in such a way that, so to find the optimal solution for this trade-off. Because otherwise there is no solution. Then this is a challenging topic that if you want to improve something, then another thing is also destroy the performance. And this is a problem we have. Okay, so what should we do? We need to look at the 4 functions. One is the transfer function LS. is try to bring the reference signal to the Y for the tracking. So you need to look at the two sensitive function for the noise and also the disturbance sensitive function. And also there is another sensitive function gives the measure process response YS to the measurement noise NS. Okay, so now you need to pay attention to the fourth function in the frequency domain. So of course, there is some background about the conceptual background coming from the both. So if you look at the both statement, because both he wrote his thesis in 1945, you see. So he published his first state of the art about the network analysis and the feedback amplifier design. So Boyd in the 1945, he introduced the topic of this function. So this is a basic, a simple case to find the trade-off between the basic sensitive function and also how to manage to do it. So the both says that this function over the frequency should be zeros and that's it. So this should be the basically the one solution basically to satisfy the performance of the system for the sensitive function. But if this function becomes zeros, then you can see that this function is an Ln function. It always should be positive, and some range should be minus, and then this becomes zeros, okay? So if you want to see that when is positive and when is the negative, so it depends to the length of S. If the S is less than 1, or if the S is bigger than 1, here you will get the positive, and here you will get the negative, and then in total you will get the zeros, okay? So these scenarios, it works, and this basically, we call it, we need to find a trade-off. So to check the performance of the system, and this is exactly the task for the design. Okay, so but if you look at this problem from the root locus, so in the frequency, so so you can see that in the Nyquist, so in the Nyquist plot, it says that the function S, sensitive function, it has for example, in this area, so is bigger than 1, and this area is less than 1. And because this should be the Nyquist function, basically for the function R and G. Or because the S, as you know, that the S is this function, S inverse is this function. Okay, so for this function, and based on the plan and the controller, so the Nyquist, the outside is a norm of S is less than 1, and then the inside is bigger than 1. Okay, so in these scenarios, you need to find the optimal parameter R, and then to see that in which frequency you want to get the norm of S less than 1, or at which frequency you want to get norm of S bigger than 1. So this was some conceptual background about the sensitivity analysis, but because of time, so I want to go a bit faster. So you can see that here we have some sort of the waterbed effect. Waterbed effect, it says that the norm of S, the magnitude, so in this area, so and this area should be enhanced, and this area should be reduced. Because here you have a peak in the S function. So this effect, if you want to improve it, so we have a waterbed effect. It's like a sensitive dirt. If you remove the dirt from one side, the dirt goes to another place. So how to find a trade-off? This is the task of the control design. And this means that we need to pay attention how to manage this function S. Okay, so regarding to the disturbance on the load, so we have this block diagram. So first of all, let's assume that there is no noise. And for the parameter ds, so you can basically find the relation between the measured signal and a state of the system and also relation between the reference signal and also the disturbance based on these two functions LS and SLS. Okay, so the RS is a control signal, is appeared in the both function as I showed you before. So now the point is that if you want to minimize effect of the disturbance on the design, so we need to pay attention the robustness of the feedback control system to the disturbance can be evaluated. So in this way. So because the system is a linear, you can impose the superposition principle. And first of all, you can assume that the reference signal is zeros and only you have the parameter ds. So the formulation between the ys and xs and also ds become like this. So if you look at this mathematical model, then you can see that the rs is appeared here. And then this model, this function can be written like gs multiplied ss, because ss is exactly 1 over 1 plus rg, okay? So in these scenarios, if you see that how the control R can affect over this performance, so you can discuss about the function ss, and then we can try to get a better understanding about the disturbance reduction. Okay, so if you look at again the same formulation I showed you before, because ys it was like this, gs, ss, and ds. So now the point is that if the norm of r multiplied g is bigger than 1, okay? So if the rg increase is bigger than 1, then you can see that the function ls, because rg increase, if the rg increase, so now you can see that the ls is approached to 1, okay? ls the approach to the 1. And what does it mean? It means that the SS is moved to the zeros. It means that the SS is moved to the zeros. And then in these scenarios, so the effect of the DS over the YS can be reduced. And this is one thing what we need basically to satisfy. So if you look at some simulation result, assume that you have a plan GS is like this mathematical model. So this mathematical model is a mathematical model for one spring and mass and damping. So one system like this. So if you look at the system like this, for example, this is a mass, a spring, and also the damping. If you look at the mathematical model for the motion of this, so this is the mass m. So now you can see that if you look at the position x for this system, so this can be modeled like this. So the model of this is a mass m, and this is a stiffness k, and also the damping c, okay? So for this system, so you can write this a function gs. Okay, so let's assume that you want to look at a stability. So for the underdamped, also the signal, the one-dimensional system, it means that this system is a one dimension. Assume that you design the control RS as a PD control. Assume that you design the control as a PD. Okay, the PD control is modeled as this. RS is the KP multiplied 1 plus TDS. This is a model of the PD control. Okay, so if you apply this control to the system and then try to look at LS and KP, now you can see that if the KP, the constant KP, so increase, then you can see that the LS also increase. But this also clear that if the KP increase, as I told you before, that the R increase. If the R increase, it means that the L is also increase. And then you can see that here you can get a better control. At the same time, this is also the phase plot. So now if you look at the function SS as a sensitive function, it means that if the KP increase, so now you see that the S also decrease. Because this is exactly you can see from this plot. By increasing the KP, So S is also decreased. So this is basically the effect of the parameter Kp. So in the for the sensitivity of the disturbance. But please pay attention that in these scenarios only we have the disturbance, but here later on we also need to add the other feature like the noise. Okay, so for this particular case, so now you can see that in the time space, if you increase the Kp, then you can see that the signal, the overshoot is also decreased and the signal becomes much smooth. So here you can see that here by increasing the Kp, so here there are some mathematical model assume that the disturbance you apply is a step function. There is no noise and also no reference signal. So if you look at the steady state error, then you can see that the error signal after some computation. So if you write it down, so the error signal becomes like this. Okay, if the Kp increase, so then the error signal, it goes to zeros. And this is exactly, you can see that by increasing the Kp, so the signal, the amplitude become less and less. Okay, so this is one of the benefits of the PV control. Of course, you can look at another effects. So from the feedback control and also compared to the feed-forward control. It means that here I discuss about the feedback control and then I introduce the L and SL. At the same time, if you can also add the feed-forward control. The feed-forward control means that if you have a plan GS, you can apply the inverse of the plant, but and then you could get exactly the same reference signal in the output, but if there is no any disturbance. But here there is some challenge. So what should be the feed-forward plan? So one case could be the inverse of the plan. But of course, please pay attention that so in many cases the inverse of the plan doesn't exist. For example, if the plan GS, it has a non-minimum phase zeros. For example, like this, S minus 1 over the S plus 1, okay? S plus 1. So this system is basically the non-minimum phase, because if you look at the root locus, so here you have 1 zeros. On the right side, it is a 1. At the same time, you have a 1 pole at the minus 1. So this system, so we call it in control NMP. So this system is NMP. NMP means non-minimum phase zeros. So this system, the inverse doesn't exist. So the G inverse S, it doesn't exist. Okay, why? This G inverse, it doesn't exist. So the reason is that here you have an NMP zeros because of this plus 1. And this plus 1 is a NMP 0. Okay, so if you want to design the feed-forward control, you need to pay attention that the GS should be MP. The GS should be MP because all the zeros should be on the left. If the system is NMP, this doesn't exist. Okay. So now most of the research you are doing so is mainly for the MP. But please pay attention that in many examples, like robotics, so the system is NNP, and therefore the feed-forward control is cannot be applied directly. Okay, but in these scenarios, as I said before, the disturbance is also appeared, and now the point is that even if you put the inverse of the G, so the output is not exactly the reference signal because the disturbance also is appeared in your output's measured data. So the measurement noise. So measurement noise, so is another challenge here we have, because assume that now you have a noise, but no disturbance. In these scenarios, again, if you write the Laplace formulation between the X and Y, and respect to the noise and the reference signal, you will get this mathematical model. So here you have the function ls, you have a sensitive function ss. So now the question is that if you want to satisfy the tracking, so ls should increase. And if you increase ls, again, you can see that the effect of the noise is also increased. So this is the problem, okay? So now the point is that how we can find a solution for these scenarios. So in this case, let's assume that the reference signal is zeros. Let's assume the reference signal is zeros. Again, you can see the relation between X and noise. So it can be written like this mathematical model, okay? So this mathematical model says that X is a minus L and S, and also the YS is the S multiplied NS. So the system response is affected by the measurement noise because the system response Y, it depends on the noise, and increasing the control gains amplify the measurement noise, okay? So that's it. If you increase basically the control gains, because if the LS increase, then you can see that the effect of the noise also increase on the, so that's it. So the system on the response is highly affected by the noise. And this is one challenge. So you cannot increase the control gains because you get the effect of the noise. Okay, so in this case, you can see that for the same example, for the same one degree of freedom system like this, if you apply the PD control, again, you start to increase the KP. So by increasing KP, then you can see that the LS increase, okay? LS increase, at the same time, SS decrease. But what is the problem? The problem maybe you can notice that at this position, if the KP increase, the SN also increase, okay? The SN is also, this is a problem because if you look at here, then you can see that if the KP increase in the high frequency or the KP, also the amplitude of the both plot in magnitude increase. So what does it mean? It means that by increasing the noise, by increasing the KP, so in the high frequency, the noise becomes more dominant, and that's it. They can, your result is highly affected by the noise. So this is one issue that we need to be very careful about the control strategy, about the parameter of the control, because all highly affecting on the response. Okay, so at the same time for this case, because of the PD regulator, as I showed you before, so this time I selected the noise like the step signal like this, NO step T. So for this case, if you look at the steady state errors, so then you can see that by increasing the KP, so the error, it moves to NO. It means that by increasing the KP, so you can reach to one error signal like this. It never becomes zeros, you see? So that's it. By increasing KP, the error never becomes zeros. And why? Because in your result, noise always exists. And this is one challenge that you need to change a strategy. You need to change a strategy if you want to get a better KP. Okay, so again, here you can see that for the measurement noise, so then also maybe bring some problem about the saturation, because if you look at the control signal US, is a minus S and S multiplied NS. So if the control R increase, if the control or the R or the KP increase, you see that if the KP increase, then you can see that the control signal, you see there is some spikes is also increased, and this brings some saturation. Okay, so now the point is that the noise, one of the issue we have, and control design issues should be fully basically to be carefully designed, specifically the type of the control. And because in this scenario, I show you that by increasing the parameter of KP, so even you could expect some saturation effects in your design. Okay, so I think we can stop at this slide because we can have a break. If you don't have any question, do you have any question or?
Sir, I have a doubt that when we are considering the two systems separately, like the measurement noise and the disturbances, so we are using the PD controller in that. So in the two different cases, we are getting two different characteristic of LS as we change the KP.
Yes, exactly. I think about your question, yes, you are right. Because here we have a three players. So two players are the bad players, noise and the disturbance. The third player is the reference signal. So here, if you want to look at the control design, you need to look at the 9 transfer functions because at the beginning, so I told you that this problem, so you need to look at this 9 function. So the question is that if you, for example, if you choose the PD control, for example, here I can write it here. If you choose the PD control, and then if you try to play with the KP, okay? So if you increase KP, then you can see that the RS increase and also this also increase. And the LS, so this is a function, it moves to 1, okay? And then you can see that at the same time, so that this makes a problem because this also also moves to 1. And that's it. The noise has a direct effect on the state. And also they bring some issues even for the control. You see that here, I show you that by increasing the RS, so here you should expect the saturation problem. And also here you will get the noisy the data in your state measurement. So what should we do? We need to pay attention to two things. Important is the how many the disturbance or the noise exists, and also about the type of the control. Because I show you here that even if you have it, for example, the noise, so you never get the error zeros because in these scenarios, always error exists. And then you need to move to the PI control, and that's it. We need to look at the PI, PD, or integration to the PID control. And then you need to play with the more parameters. So with one parameter and also two players or the three players, is difficult to get a good performance. So, but of course, you need to always pay attention that what is the range of the frequency of the noise in the low frequency or the high frequency, and what is your bandwidth and how to choose the control parameter. So this example or this question, so it in total is some sort of the trade-off. You need to pay attention that how to mitigate the performance by changing the three parameter or two parameters. So here I talk about KP. So if you change it, for example, to the PID control, if you move it to the PID control, then you have a KP, KI, and KD. Or even you can look at the PI control, then you have only the KI. So now the question is that the selection of the regulator RS is very competitive because it's directly could manipulate the effect of the noise, manipulate effect of the disturbance. At the same time, your target is the tracking, for example. So in this case, we need to very pay attention. So, but this is a question always exists in the control design, and of course there are some other issues. Maybe we can discuss after the break. But of course, you can always contact me, or I can provide you all the materials. You can look at this lecture note after the class. Do you have any other question or?
No, sir. Thank you.
Okay, I think based on a schedule, so we can have a short break. So I think let me look at the schedule. So I think
Yes, sir. Can we have 10 minutes or 15 minutes break, sir? Depend what decide, sir.
okay, then we can have a 15 minutes break. we can start after at 12. Okay, 12 in Italian time means 3:30 p.m. Okay, maybe 12 minutes
Yes.
break is okay. Okay, see you soon. Okay, thank you.
Yeah, thank you, sir.
Thank you. Thank you.
So participants, you be online.
Yes.
You can have your tea or water, whatever. Although it is not here in the department, so you can have your tea quickly, and please come back at 4:30 IST. Good evening, sir, and welcome back.
Okay. Thank you.
Dipan this side, sir. Sir, I have sent you a mail. So whenever you get time, sir, please.
Okay.
That
Thank
was
you.
that was regarding the feedback form only, sir. On final
Okay.
day, we required it, sir.
Okay. Thank you. Okay. Then
Thank you, sir.
if there are any questions, please let me know. If not, we can continue. So I try to cover this part and then to go to the another control strategy as a control the slightly more control. But we discuss about the design issues. We noticed that we have a three players. We have a noise, the disturbance, and also a reference signal. And in the linear system, so basically we are dealing with the 9 transfer functions. Then we started to look at some particular cases. So this was we discussed before the break. So, okay. So if you look at the measurement noise, so in the context of the feedback and also the feed-forward control, so basically we need to look at the two functions. One is the state, one is the measure signal, YS. And then we notice that in the existence of the reference signal, the noise and both exist. It is a challenging topic because if you want to increase LS, noise is also effect is also increased. And this is a big challenge we have based in the state. And also when it comes to the measurement signal, so we need to pay attention that how to increase L and how to decrease S. These are the issues in the feedback affected by the control parameter KP. At the same time, if you want to look at the feed-forward control, as we discussed before for the MP, so it means that the major signal consists of the noise, and the noise cannot be manipulated by the controller. So it means that the noise is directly appeared in your major signal. So for this particular case, so the feed-forward control has no such a robustness respect to the noise, and then you need to look at the robustness with the feedback part. But what's the benefit of the feed-forward control? Just to improving of the performance, and this is basically not affecting on the stability. Okay, so the effect of the transducer dynamics, if you look at the sensor model, so if you have a function TS as a transducer model or the sensor model, then you can see that only the function LS is changed to this. It means that the function TS is appeared also in your function LS. So this is the basically we have from the Laplace domain, and it means that the loop gain, if you look at the loop gain, so is the T multiply R multiply G. Okay, so I give you one example about the effect of the transducer dynamics or the sensor. This is the topic is about the sensors. Okay, in the sensor, one parameter is about the delay. Okay, so assume that this is your physical plant. This is your controller. The control is a P control as a P regulator as a control P. So the function Ts is appeared as exponential for e power of minus tau s. It means that you have such a delay as a parameter tau, and if you give the sensor the state xt, and here you will get basically here you have xt, and here you will get basically the x. So size x. And here you will get the x t minus tau. Okay, x t minus tau. Okay, so now the delay is appeared basically appeared in your output. Okay, so in the function is the e power of minus tau s, and then when it comes to the linear analysis, we need to approximate it. And one approximation for e power of minus tau s, approximation is e minus tau s. So when you approximate this function by the linear form, then you can see that the delays appear. But this parameter, it brings a lot of difficulties, because this gives you the exactly the zeros. If you look at here, this gives you the 1 zeros at the s over 1 over tau, and I can explain you later on. But let's continue. So if you look at the function ls, if you look at the function, the loop gain ls, so based on rg, trg, then you can calculate it from this expression. You will get this function, okay? So in this function, you can see that a stiffness becomes k plus kp if you are using the p control, because here the regulator rs is a p, okay? Regulator is a p. And then the point is that the damping, it becomes c minus tau kp. So in mechanics, it's very important. In mechanics, it says that if you're adding the delay to such a sensor delay, so the damping decrease. So if the damping decrease because of the effect of the kp, effect of the tau, what's the problem? The problem is that if the damping decrease, the phase margin decrease. If the phase margin decrease, the system potentially become unstable for the large kp. So it means that if the gain kp increase over a certain value, the system become unstable, this instability. So now this is very important. So now you can see that because of the delay tau, now you can see that by increasing kp, so the damping, so this goes down. And if the damping goes down, so the phase margin in control, it means the phase margin also decrease. So if the phase margin decrease, so it means that stability also decrease. So stability also decrease, because if for some certain kp, the system become unstable. So this is exactly the problem why the delay is a challenging topic. So now you can notice that by having a small delay, so the system stability become questionable. Okay, this is a simulation result. Then you can see that for the same system, if you have a P regulator as a P control, so if you increase kp for a small delay, for this delay 0.025, so if you increase the delay, the system become oscillator, and this is a potentially unstable case. So as a summary, in the summary, we talk about the two functions as a sensitive function SS, and also the complementary function LS. So the summation is 1, and it means that if the L increase, S should decrease, and that's it. So we need to look at the load disturbance attenuation effect. It means that how the SLS, so it can be attenuated. You need to look at the effect of the measurement noise can be handled to S and S, and this the function also should be controlled. So now the question for you is that if you want to do the tracking, if you want to only reduce the noise effect, or if you want to only reduce the disturbance effect, so what kind of control with which parameter of the Kp, Ki, Kd. And this is a traditional control basically we have for the physical plant. Okay, so we notice that the delay is important part, especially the sensor delay. And then you need to pay attention that how to look at the function SS to improve the performance. So, but another important topic we have in control is the combination of the feedback and also the feed-forward control. So, but usually in all the control textbooks, they focus on the feedback control. But if in the future, if you do some project specifically for some project related to the oil company or the oil and gas business, so most of the industrial plant they have in the oil company is based on the feed-forward control. So now you can see that the feed-forward control is also important from application from industry. And that's it. It's good to know how to combine the feedback and the feed-forward control. Okay, so I think I can skip this part. I can provide you this example, but because of time, I'm going to the control strategies. So in the control strategies now, we have a feedback, we have a feed-forward, and we have a feedback and also the feed-forward control. Okay, so I show you some scenarios of how we can reach the combination of the feedback and the feed-forward control. Assume that you have this system. So this system is a 1 degree of freedom model. It's a single degree of the vibrating system. This is a mass. This is a damping. This is a stiffness, and this is a force. This is the control force. So if you look at the hypothesis, the system is stable, and we are looking at the underdamped single degree of freedom vibratory system. So underdamping means that the damping factor, the T psi, this should be less than 1, okay? Something like this. And also the objective is the fitting in the mechanical system with the force FC. We need to design the force FC such that this mass, the reference to follow the reference signal ZREF. Okay, so we want to see that how this mass position, the center of gravity of mass, how this parameter Z, so they can follow for example, the reference signal ZREF, okay? So this is basically our target. So you can write this mathematical model, and this mathematical model based on the mass damping and also a stiffness. There are two forces, F and Fc. So the force Fc, as I said before, is a control force you need to design. So there is another force as a force F. So this force F you can see here. So is composed of Fd and also Fr. Is not some external force. Okay, some external force or the resistance force so can be also added together as a one F we represented here. So the question here is about the FC, because if you want to design the control, you can design either the feedback control, feed-forward control, or the feedback plus the feed-forward control. Then I want to show you that different design. So one design is like this. So this is your mechanical system. So I to show you before, this is a function model of GS. So you need to design the control. Assume that you design the PD control, okay, the partial derivative control. And the partial derivative control, so if you want to see the formulation between the error signal and also FCFB, so this formulation is valid. FCFB is a KP multiply ZR minus Z plus KD multiply this. Why? Because the force, because of the PD, you have here, you have a KP, you have a KP multiply E, Okay, I think I need to change my mouse. I think my mouse is not working properly. So here should be KP multiply E plus KD multiply E dot. So, okay, KP multiply, this is a E dot. And this is also the E, okay? Okay, so for this case, if you look at this mathematical model and if you put it together, all the terms, so you will reach to this formulation. So FC, so is equal FP, FT plus KP multiply ZR plus KDZ dot R plus this term. Okay, so this term is a contribution from the reference signal because here you have a reference signal ZR. So this term, this remains, that this system remains because this is some constant term. But this term depends on the dynamic of the Z and position velocity. So you can bring it this to the left. And if you bring it to the left, so then you will get this mathematical model, okay? So in this mathematical model, so here you have basically the change of the damping, C plus KD, and here you have a K plus KP. So this is a very important. So basically, when you design the PD control, so you are changing the damping and also you are changing the stiffness. And that's it. You need to pay attention that how much you need to change KP and how much you need to change KD because you are modifying both parameters. So when you design the feed forward control, I told you before that the feed forward control, so this should be the inverse dynamics. So this should be the inverse dynamics. So it means that even if you have here the G, so this should be the G inverse. This should be the G inverse. So G inverse, but I cannot write it properly, but okay. So, but anyway, so the inverse dynamics, so can be written like this. So but the point is that here there are three parameters, M, C, K, and also in the inverse dynamics, you need to change another parameter as a M hat, C hat, and K hat, because you cannot exactly write the same model because this is your exact model, MCK. But when you want to write the inverse dynamics in the time space, you need to choose another parameter M hat, C hat, and K hat. So this is a question because this parameter should be estimated, but if you don't have the exact parameter, then you should put some estimated values, okay? So, but if you choose this mathematical model for the inverse dynamics, so then here you can calculate the FCFF. FCFF can be calculated, so from this mathematical model, and so you can write it like this, okay? So what happened here that, so here you just follow the same shape of the system dynamics, but with another parameter for the mass, another parameter for stiffness, another parameter for the damping. And this could be your inverse dynamical model. And then you can combine this inverse dynamics with the mechanical system. And here you have also additional force F. Okay, and this force F, you remember that this is F is FT plus FR. And here the FD is coming from the basically from the inverse dynamical model. And then if you add it together, then I will show you in the next slide how to combine it. So it means that for your system, for the first system dynamics you have, so here you need to substitute FCFF as a feed-forward control. So basically from previous slide. So this is your FCFF. You can put it here. And then this kind of the disturbance. So this one is also goes with the disturbance here you have. So here, okay, with this disturbance FD, so this can be removed, and then you can write this mathematical model. So in this mathematical model, so in this mathematical model, you can see that there is some changes basically in the change of the mass, in the change of the damping, and also in the change of the stiffness. And basically, there could be some mismatching between the parameters. So, okay, so I try to change my mouse just a moment. So basically, Okay. Okay, so now you can see that by adding the two different masses here, so the M hat and C hat and K hat, so basically we got some mismatching between the real mass and also the mass we have used it basically in the model like this. Okay, so now if the M hat is equal M, C hat is equal C, K hat is equal K, it means that you have a perfect matching. But in reality, you don't have a perfect matching, and that's it. You need to accept some uncertainty or some changes in the parameters. So the feed-forward control does not modify the system parameter and does not influence the stability, and only the feed-forward control can affect on the performance, and that's it. So one question in all of the design is how to choose the parameter and also what are the effect of this parameter over the overall the performance. So this slide shows that the combination of the inverse dynamics, the feed-forward, and also the feedback control, and this is a mechanical system. And then you can see that by adding the feed-forward control, you can enhance the performance analysis. So basically, these are the mathematical model. They are representing basically all of the equation. So if you want to do like this, so from the writing the mathematical model, you need to write, for example, to these scenarios. But here you need to pay attention that here we have used the PD control, but you can use different control, like a sliding mode control or any other control, and then to see what is the result. And this is the question usually when I'm teaching this material to students are free to choose different control. So, but of course, we can start from the PD first, and then as a baseline, as a classical control, and then to move on to the other control. Okay, so the very important conclusion is this. If you combine the feedback and the feed-forward control, please pay attention that feedback control, they try to change a stiffness and change the damping. It means that you can enhance stability. On the right side, if you use the feed-forward control, then you can add additional term for the better tracking, for the better performance of the system. It means you have a sort of some mismatching between the different parameters. So it means that the combination of the feedback and the feed-forward generally allows to obtain the best system performance, and that's it. If you go to some industry, I always say the oil company because I did many projects with the oil companies. And I can tell you that all of the oil companies, they only mainly interested to the feed-forward control because it's very simple. At the same time, they can also get a good performance. But what about stability? Because in that business, stability is always guaranteed and there is not so much concern. But okay, so this could be one scenario I had to try to explain, but there are some examples like the robotics. So in the robotics, if you start to mathematicize this dynamic of the robot, so to do some task, for example, to do some sort of the following some particular position or the angles or particular velocity or particular acceleration. So it means that for this system, for example, if you look at this rotation of this pulley with this kind of a spring and mass, and it means that if you look at the particular rotation of this pulley, so you need to pay attention how to design the control F, for instance. But if you want to satisfy for example, the tracking, you need to pay attention that if you are using the PD control or other type of control based on what I presented now. So at the same time, there could be some loading or the disturbance over the plant, and that's it. So we need to pay attention that how to basically to look at the effect of this kind of a disturbance. Okay, so it means that for this model, so if you start to mathematicize, if you want to have a rotation tau for the position tau, and based on this control signal in C, for example, if you are doing the feed-forward control, as I told you before, that for this dynamical model for the rotation of the pulley, so with this inertia, damping, and stiffness, so you can obtain this feed-forward control with the J hat and also as the C hat and K hat. But the shape is the same shape. You see the same mathematical model, but only change of some other parameters in this model. Okay, so if you start to find a transfer function, so you can basically apply the feed-forward control to the system like this. It means your reference theta to the final theta, and then if there is no external force, so then you can basically get this mathematical model. If you have a perfect matching, what does it mean? If the J hat is J, C hat is C, and K hat is K, for the perfect matching, you can get the perfect tracking. But of course, if you don't have the perfect matching, you cannot achieve the perfect tracking. So if you want to design the control, the feedback control, you can use the PD control, okay? If you design the PD control like this, then you can obtain the same function LS like this. So what happened here, that here you can see that in this function, so that you can get the effect of the KP and KB. So basically in your stiffness and also in the damping, and it means that stability can be improved. And then if you combine it with the feed-forward control, you can also enhance the performance, and that's it. So the combination of the feed-forward and the feedback control, so basically if you follow this mathematical model, is very simple, but if you start to write it down, so for this mathematical model, there are two forces, the feedback and also the feed-forward control. So basically, so you can obtain it from these two expressions, and then you can close the loop. Okay, so this strategy is the feedback plus feed-forward control, and in many applications gives a lot of benefits. So again, I can repeat it again. So if you are doing in the Laplace domain, so here KP, the PD control is this. This is your plan, and this should be the inverse of the plan. But please pay attention that not exactly the same G, it is a G hat S. Okay, so if you start again to write down the expression in the Laplace domain, so you can write a theta S relation to force and also the feedback and feed forward the forces, and then you can write it down the expression between the theta and also the reference signal. So based on this formulation. Again, if you have a perfect matching, the theta is exactly theta R, but we need to pay attention that we never reach to the perfect matching because we don't use exactly the same exact parameter of the plan. But from the mathematical aspect, this is the analysis. Stability can be enhanced based on the control feedback, and also performance can be improved based on the feed-forward control. For instance, this could be your the reference signal and also velocity and acceleration, and then you can basically, if you have the feed-forward control with the perfect matching, J hat is J, C hat is C, K hat K, you can see that you have a very nice tracking to one. It means that your performance is perfect because you have a perfect matching. But if you have a feedback PD control only, if you have only PD control, then you can see that for this reference, the response is a blue one. There is some drift. You can see the reason is that the PD control cannot guarantee the perfect tracking. Only stability can be improved. But now you have some offset in the tracking. And if you combine the feedback and the feed forward, so for the perfect matching, then you can see the very nice result. How we can achieve this good result? Because the feed forward, they can try to enhance the tracking, and the feedback can enhance the stability. And this is the main idea behind of this motion control. Okay, so if you have an underestimated stiffness, for instance, if the K hat is a half of the K, then you can see that you never reach to the target, and you have some drift in the response because you have an underestimated stiffness. And then if you have this for this underestimated stiffness, if you apply the feed forward and the feedback, again, you can get a better result, you can see. But if you have a better estimation, better result. So this means the knowledge. If you have a good knowledge of the system, you can get a better design. But if you have a less knowledge, you mean you are always is the underestimated case, and that's it. The performance is never reached to the ideal case. Okay, so these are the result of the PID control. For instance, for this particular case, these are the response and also the response of the feedback and the feed-forward control. You see that the green line, so the combination of the feedback and the feed-forward gives the good result. So basically, compared to only the feedback or the PID, and this means that we can get a better result if we move on to the combination of the feedback and the feed-forward control. So in the case of the basically the response, if you have a disturbance on the load, assume that you have a disturbance at the time 2 seconds, and then you can see that this disturbance can be compensated, you see. So they basically based on this design, and this means that the system has a good robustness, basically based on this strategy. Okay, so this is also the measurement noise. If you have a measurement noise, the measurement noise with this kind of the variance, so you can see that the response, the blue one is like this. It means that we have this kind of the measured data. This is it, and also this is our the blue one is our response. Always we get some drifts because of the measurement noise, and again we cannot reach to the perfect tracking, and this is also the effect of the noise. So basically can be appeared. So the measurement, you can see the green signal because of this noise, you can see. So at the time 2 seconds, you have some peak, some jumping, and then this can be vanish, and then but of course the response remains to some offset because the noise exists forever, you can see. But this is basically you can analyze the effect of the noise. So as a summary, the feedback and the feed-forward control could give some advantages. So compared to each of them as a separately, because you can improve the stability, you can also improve the performance. But this is a design as a sequential design. It means that you can first design the feedback control, and then after design the feedback control, you can come to design the feed-forward control to get your desired response. So this means that only the important thing in the feed-forward control is the good knowledge of the system, because you need to have a good matching of the performance. Okay, so based on this discussion, we can a little bit talk about the resilience. So for this system, because the resilient system, control system, so basically in different applications like a power electric, the water-based system, oil, telecommunication, you can see that the ability to the network control system has provided a mixed blessing in the ability to interlock the system of systems. So the system of system. Okay, do you have any questions?
Sir, Dipayan this sides. Just I have a very small query, sir, related to the feed-forward control. So as we know, sir, and even you also have mentioned in your presentations that the feed-forward control requires the knowledge of the systems, explicit knowledge of the systems. So, getting the knowledge or informations of the disturbances which is coming to the plant So that is practically not possible. So in that situation, how can we proceed for the designs of the feed-forward control?
Oh, thank you. This is a good question. Actually, when I'm talking about the knowledge, I'm just talking about the physical parameter knowledge for the system. I'm not talking about the disturbance or the noise, because the feed forward is only needs information of for example, in this case, you need only get information of the G hat S. And in this case, only the important information is the physical parameter, like the mass, the stiffness, or damping. So now the other parameters or the functions or the disturbance noise is not part of the knowledge. Yes.
Okay, sir. Thank you. Thank you, sir.
Okay. Okay. You're welcome. Yes. Okay. After this discussion about the complexity of the system in the control design, we need to look at either the feedback, feed forward, the mix of the feedback and the feed forward. And because from application is very important, because I'm not sure which kind of the business you want to do or currently in the future. Many industries, they need the feed forward control knowledge. And that's it. We can come to the another topic about the resilience. Resilience means that there is a system at any time is a system of systems. So one keyword here is a system of SOS. So the topic of SOS is also the part of the CPS, and it means that basically we need to pay attention that how to basically we can look at the SOS in terms of the resilience. So because the system are connecting and also the even in different crossing industrial sectors, so the control system complexity basically exists from different aspects as we discussed today. So cybersecurity is also the part of the resilience because the system potential is under threat. So from different sides. So you can see that in this graph, this is some basically some attack sophistication. So from, for example, 1985 to up to now, for instance. So you see that the sophistication of the attack increased. And that's it. The system potential get a lot of unknown attacks, and that's it. How the resilience or how to look at these cybersecurity attacks is very complex, and that's it. We need to include some more resilience in the control design. Okay, so if you get the targeting of the complexity in the control system to the more secure control system or the more resilience control systems, you are trying to deal with the complexity of the cybersecurity attacks because it's growing very, very quickly. And this means that we need to pay attention to these aspects. So even another today, I talk about the human machine interface, because as I told you that in Industry 5.0, so the human system complexity is the major task. How to model the human in interaction with the machine. So now you can see that the human interfaces are loaded with the data. So now you have a data and the complexity of the gathering of the data for operator or dispatcher to interpret, how to interpret the data. So this interpretation, and this is the kind of the interaction between the human and also the machine based on interaction cognition. So today I discussed, I told you the HMCI. So the human machine cognition interface, HMCI. So HMCI is a very important topic in Industry 5.0. Not only human, not only machine, but also the cognition, perception, how will be added. So if you are interested, because in my group, we are working on autonomous driving. Autonomous driving, one aspect is the driver interaction to the machine, not only the physical driver, but also some perception, cognition. So this means that the sensor actuator, cognition, interaction with the machine, processing, all is a complexity we have. At the same time, so this complexity from this HMCI, you need to pay attention also from the cyber security, and that's it. Nowadays, if you talk about autonomous cars, cyber security is a very important topic. And I'm sure that in India, maybe there are many companies that are producing the cars. And for them, it's also very important how to implement not intelligence, because intelligence, autonomous driving is becomes practically feasible, because everyone can develop a lot of machine learning tools for the car driving. But what is important is the integration of the cyber security and also the machine learning for the or AI in the autonomous cars, because here we are talking about HMCI, human machine cognition interface, and this brings a lot of complexity we have in the resilience case. Okay, so there's some consideration arising from the complexity, unexpected condition adaptation. So I told you about the autonomous driving. At any time you have some unexpected conditions because environment changing, you have an uncertain environment. So distributed control to address the complex interdependency and the latencies, the composition of the interdependent control system elements to simple stabilizable agent. So because you know that this kind of the system is a system of system, I told you that this is SOS. So for the case of SOS, you need to have some strategy to control the system at the different levels. So for example, in the context of SOS, so another topic becomes important is the multi-agent, okay? So when you talk about the multi-agent, so multi-agent. So for the multi-agent system, because the agents are collaborating, the agents are competing, then you need to control the different layer of the agent. At the different layer, you need to control, and that's it. How to stabilize? These are the some issues we have in the resiliency of the control. It means that in this context, you need to look at the hierarchical distribution of the agent. At what is which task is the higher priority or the importance. So another topic is about the goal conflicts. You need to recognize the performance goals about in addition to stability, the security, efficiency, and other factors. You see that today we discussed about stability, performance. Now we need to talk about security, efficiency, and other factors. So overall, the criteria for the performance of the control system must be prioritized with the appropriate trade-off analysis. So now you see that the trade-off is appeared, because the resiliency, always you have a trade-off, and that's it, because you have another player. Another player is the attacks. And attack is the uncertain, is the unknown effect, and that's it. How to look at this trade-off is the important part. So you need to enhance the system awareness. It means that by looking at your data, and for the data sharing, and if the data want to be circulated, to be translated to the information, so you need to pay attention that this translation to information based on some condition of the process and control system component. And we need to be aware of the data, because in the data awareness, important is that you need to trust. You need to trust your data. And if the data is attacked, if the data, there's a malfunction in your data, if you don't trust the data, then the data cannot be transferred to information, because transformation or translation to information means the control, okay? So because what we are talking is about control. So this translation to information is control, because control is information. And you can apply to the plan. And if you apply the wrong information based on the manipulated data, but this is a very strange or very important challenge. Another topic about HMCI, the human interaction. So as I told you, that the industry 5.0 is exactly this topic about the human performance prediction, cyber awareness, and intelligent adversary. So now you see that in the resilience context, there is a lot of consideration we need to pay attention. So these are the some topic about the cost, the policy benefits. If you want to get some resilience metrics in the measurement, if you want to get some resistance in terms of the resilience design, you have the cyber control and the cognitive, you can get against some resilience design. So if you want to come to the consensus, so in terms of the recount for the CPS, you have a cyber, physical, and cognitive. Then you can get some state awareness and as a recount for the CPS. And then if you want to come to the resilience, you have a resilience design. You need to get a resilience design, a state awareness, and the threat information. Then you can get some basically some by developing some accountable information, adaptive architecture, you can reach to the resilience. So now you see that measure, respond, recount, and resilience. There are 4 disciplinary and also in the context of the resilience of the CPS. Okay, so the you see that there are some statement. It says that next generation, the control system from reliable to resilience. So there is a very good definition. So basically it says that the resilience is the capacity of the control system to maintain a state awareness and accept the level of operation normalcy in response to the disturbance, including the threats of an unexpected and malicious nature. So this is a very standard definition we have. So now the capacity of the control, the resilience control, and also how to keep the state awareness. This is basically the one of the important challenge, because resilience, you need to enhance the reliability, and because you need to look at your reliable information. Reliable information, as I told you before, is coming from this awareness, state awareness, because if the data want to be changed to the information, you need to look at the reliability. You need to trust, and that's it. Reliability to resilience is an important topic we have in the resilience control design. Okay, so there are some transformational threat resilience control system in the national challenge about the cascading failure, cybersecurity. And also there is some addressing challenges as an outcome. It means that how to minimize the impact to infrastructure and mission, intelligent architectures, diverse detection and the response protection at each level of the control system architectures, advanced control design. So basically they could assess degradation and the proactively control, cyber security and human factors. So now you can see that the challenges we already know about it, some failures, some attacks, and the cybersecurity, and the outcome to enhancement. And this means that one of the important part is from the control, and we try to discuss it. But very also briefly, because reliability is one of the very important topic in the resilience control, because we are talking about the data translation. So, but one aspect today we talk about the centralized and also decentralized or the distributed. So you can see that if you have a reliable, centralized to resilience distributed control, so there are some comparison in the state of the art. So one issue is about the unexpected condition adaptation. It means the centralized monitoring and control interactions that are brittle to unexpected failures. So it means that if you talk about the reliable for centralized system, there should be some complexity, interdependency and of interaction that cause emergent behaviors. So human interaction for the reliable centralized case, it means that you can look at basically the common complex human performance variables and variation. But when you talk about the resilience distributed control, even for the same human interaction, you can look at the prediction of the human performance. and also autonomy interdictions. So, or the fusion and the prioritization of the response based upon resilience priorities. So it means that for each category, for unexpected condition adaptation, human interaction, even the malicious actions, because in the reliable centralized, you have a lack of a state awareness of the malicious actions. But if you come to the context of the resilient distributed control, so basically we have some active defense and also for deception, environment modification. So now you can see that adding the resiliency to the distributed control, you can get a better approach to deal with the active defense respect to the malicious actions, better prediction of the human interaction, and even you can come to the some sort of intelligent behavior for the unexpected condition adaptation. So in total, we can get a lot of benefits. So of course, we can discuss more details. So for each part. So if no question, I need to switch to another topic. So because we have another topic we prepared it for today.